Abdul on the phone, or
Yes, he's on the phone.
Yes.
Tariq? How are you? Thanks for doing this.
Oh, no problem.
Uh, how can he see you? He's seeing
Yeah,
us.
he's gonna see me right in front. Here. Do you see me, Dr. Abdul?
See you, I can see the slides. I can see also the committee a little bit.
Okay.
So you're using this top camera to see us. Okay.
So we are waiting for Professor Gupta, who's gonna be here in 2 minutes. I don't know if we can start or
You can start by introducing yourself.
do you wanna introduce the committee?
Yes. So, Tariq, for your benefit, we have with us. We're waiting on Professor Gupta, who's going to walk in any second. He's from mechanical engineering. We have Professor Hussein. Hussein, you want to raise your hand so can you see you? He's environmental geotechnology, and he's our graduate advisor. You know me, and Stephen Bless, who is a physicist. He's in the blue shirt, and has been working with us on penetration problems for the last how many years, Stephen? 6 years?
3. Well,
No,
but
starting
here
in
3
Texas.
years. Yeah, longer before I came here.
Yeah. So he was at the Institute of Advanced Technology at Texas, UT Austin, and when that institute was moved from UT to Southwest Research Institute, he joined us here at NYU.
Hi, everybody.
Hi, Dr. Abdul.
And Eduardo has been here for exactly 5 years, correct?
In January.
In January, he got his undergraduate education in La Salle University in Colombia. He did a master's degree or some graduate education in Colombia, a master's degree at UT Arlington, and he's now defending his PhD. This is Professor Nikhil Gupta from Mechanical Engineering, who's an expert on dynamic loading of materials. I'm sorry, I was on the phone. So with us on the phone is Professor Tariq Abdoun, who is now you're what, Associate Dean of Engineering at RPI, as well as a former department head. He's well known for his research in geotechnical engineering, particularly centrifuge modeling and sensing, among other things. There's a number of students that you see that will invite for the presentation, but they'll leave during the questions. He's on the camera. All right, Eduardo, you have 45 minutes, I think tops.
With no more introduction, I know you all know me already. It's been a rough week. We just had a second baby 5 days ago. So I think that this is going to be just for the wellness of the family. The name of this presentation is just a summary of 5 years of intensive work. I've been working with the mechanical behavior of grounded material that is being loaded at different strain rates. I name it a study of the strain rate effects on the mechanical behavior of sand. This is the outline of the presentation. I'm just gonna leave you to read this 5 to 10 seconds. The main goal of this research was to experimentally to understand the behavior of grounded materials that are exposed to, I would say, low, intermediate, and high strain rate monotonic loading. It's not dynamic, it's not cyclic events, but monotonic loading, and also including the role of particle breakage or particle damage in the behavior. Some of the applications, obviously, military applications, explosions, mineral and mining engineering, ground improvement, static and dynamic compaction, geotechnical and petroleum engineering, astrology and planetary studies, and powder technology. The motivation or the background of this work Quickly, this study, or the study of the strain rate effects on the behavior of sand has been conducted extensively in the past. However, some observations are contradictory. Some results claim or suggest that it has significant effect. Some others, on the other hand, I state that this increment is very little or negligible. I will see, based on my results, what we can control. The role of particle composition and particle breakage in strain rate dependence it hasn't been well investigated, indicated. And very few high strain rate testing interaction compression conditions have been conducted. So for which I can say the mechanical behavior under of these conditions is still incomplete, and there is enough room to keep investigating. This chart indicates several regimes of strain rate. You can see here. So okay, in the first row, we can see several regimes: static, quasi-static, condition dynamic, and very high impact events. Several different actuators which we can use to achieve those strain rates. And where I wanted to point, this is important, where the inertial forces are negligible and where the inertial forces are important. So the main regime where I've been working on is typically in this part, in a strain rate that runs from 0.01% per second up to 100% per second, plus a few more studies to achieve higher strain rates. Obviously, before starting the experimental program, we conducted an extensive literature review on the high strain rate testing techniques on sand specifically. We went through several different loading mechanisms, several testing techniques, issues that tests and experiments at these levels where inertial forces are important were documented. And this was a publication that we have so far in the ASTM geotechnical testing. These are the four main stages of this work. The first one is to experimentally to evaluate the rate effects on the behavior of sand under uniaxial compression test. The second one is, again, the strain rate effects in the global behavior on the triaxial compression conditions. Based on these two main results, I was able to develop, based on existing theories of strain rate energy density, to develop an empirical model to predict strain rate strain behavior. And the final stage was is the role of particle damage and strain rate on this strain behavior of sand. This slide depicts the materials that I use. I use a siliceous sand and calcareous material. I hope you can see these. These are the main physical properties that depicted for both materials: the coefficient of uniformity, the curvature, the classification of the material, SP, it's a poorly graded sand. And we can see here the two size distribution and the aspect ratio that are very similar to each other. For the first stage, experimental work by using uniaxial compression test was done by using a hydraulic loading frame. I run 4 different strain rates, quasi-static to intermediate strain rate, from 0.01 up to 10% per second. In civil engineering or in geotechnical engineering, the regimes for the strain rate might be different than those from physics or mechanical engineering. So for you, having this 10% per second as a intermediate strain rate might not be true, but for us, since our applications are more not quasi-static, but we are not expecting to have applications with higher strain rate loading. Two different materials, made at very dense condition, obviously using the maximum and minimum density that comes from the ASTM standards. Repetitions, like in order to find out the repeatability of the experiments, for a total of 32 good samples. Out of these 32, or besides these 32, like I think I ran like about 100 tests in order to find out which ones are good tests. So we use this hydraulic frame, and I also created a like 6 inches steel mold to house this material, and plus the cap that is going to be on top of it, that is going to be the transition between the RAM and the material. And it's uniaxial because we are preventing lateral deformations, or we have these conditions radial. So after these 4 tests per each condition, right, we were able to, or I was able to plot them together at different specific characteristics, such as for silica sand and for coral sand, we have 4 main strain rates and 4 main strain rates. They are from 0.01 to 10% per second. So the red dashed lines are experimental results, and the solid black line represent the mathematical average of them. So, but then at the end, we can plot the average of each one, and we can see that here there is a small, some sort of an increase on the thickness and the final strength at the end of the final actual strength, here and also here. If you notice, the slope might be different. And also, I run like a few verifications to check that the strain rate that I targeted with my samples were really experiencing these strain rate conditions. So you have the time, or we have the time, again, the target strain rate. By doing the calculations, I was able to check that this strain rate here is constant for this, for this, for this, for this, and also for 10% per second. The steady condition of the loading for this small period of time was achieved, whereas for 100% per second, which is a limitation of the device, this curve didn't reach to this point. That's why I decided not using the hydraulic machine to run tests at 100% per second. This is a similar stress-strain curve that shows actual stress versus time in log horizontal scale to see the difference between silica and coral sand, silica and coral per each strain rate conditions. And then after that, the constraint moduli that was taken from 5 to 10% actual stress per each condition gave rise to the conclusion, the initial conclusion, that we can see a small or some sort of an increase of the stiffness of the material as the strain rate is increased. Now, for triaxial compression test, the same loading mechanism by using a hydraulic actuators. Now, the main difference, obviously, is that we don't prevent radial deformation. We allow it to take place. If you can see the difference between, ideally, in traction compression versus uniaxial compression. In traction compression, we are expecting a failure of the material as a whole. After the peak is reached, right, the material is going to experience a critical state or ultimate stress somewhere here. Whereas in uniaxial compression, it is a combination of initial elastic deformation, rearrangement of the particles. Eventually, if the load is sustained and increased, particle damage might take place, a new rearrangement is expected, and so on and so forth. So for 3D or for traction compression, again, I have 4 different strain rates, the same ones. Now here, I tested 2 different density conditions. Very dense, which is plus minus 85% of the relative density based on the maximum and minimum densities. And for loose conditions, 55, that's loose to medium dense. In those 2 materials, and now we have 3 different confining stresses, 100, 200, and 400 kPa, added 3 repetitions per each condition for a total of about 32 some to understand or to go through this behavior of the role of the fast loading rate on the global behavior of sand, we have submitted for the standard publications again to ASTM Geotechnical Testing Journal, which is under review right now. And the main idea was to discuss inertial effects, the global versus local strains, which is important. Now that the sample is slender, so it is not as thin as an uniaxial sample. When the load is applied and a constant loading rate, we are not guaranteeing that the strain rate is going to be uniform across the entire sample, even though we have a higher strain rate. Not this magnitude of a strain rate. So that's something that we have distinguished. Again, observation is in stiffness, observation is in shear strength, and the role of particle damage under these conditions. One of the first steps was to verify inertial forces acting on the specimen when the sample is loaded. And what we did was actual strain versus time. Ideally, the curve should be linear, but if we take a close look on the first, like half of a second, or in the first 20, 200 milliseconds, right? We can see a small concave path behavior here that might be related to initial small inertial forces in the beginning. But for the rest, we have a very well-defined linear deformation. Now, these are the averages, the plot of stress-strain behavior. Now, and remember that this is, we have 3 main confining stresses conditions: 100 kPa, which is the first row, 200 and 400 kPa. And also on the left side, on the left column, we have a very dense material, 80%, 80, 85%, and on the right side we have 55. So we can mention now that this is dense and this is loose. Now, the different colors and the different type of these lines represents different strain rate conditions. Again, from 0.01 up to 10% per second, we see nothing here, or it's not that we don't see anything, but we see a negligible effect of a strain rate. We don't see much here either. We start looking at some effects, small effects, but it still is not really like well defined. The same here. And now, when the sample is loaded at a higher confinement stresses, we start looking at something interesting, which is well-organized terrain that where the the slowest phase is going to be at the bottom, and the fastest one is going to be on top. And it's more evident when the density is higher than when the material is loose. So in this material, which is a siliceous sand that has these shapes, and that has like some sort of a well-defined cleavage when the particle is broken. On the other side, we have a coral sand of calcareous material, and we have these two conditions. We saw these two density conditions: dense material, loose material. I only got here 100 and 400, and in 100 kPa of confinement, again, it's not nothing in terms of strain rate dependency is seen, but here it's different. Now, it brought my attention to see this huge peak of the deviator stress, and then after a sudden drop and significant drop after the peak, that at the end they all go and follow the same ultimate stress. Looking at literature and previous studies, I found that the cementation component on the material, believe it or not, calcium-based material, might induce or might provide cementation effects. I noticed that also after when the load is when the test is finished, the particles of the material are bonded together. Things that don't happen, that doesn't happen when you have silica material. Now, based on these previous tests, we thought, I thought the variation of the secant modulus of the elasticity versus the strain rate in these two on the left side of the screen. Silica sand on top, coral sand at the bottom. And to see how this strain rate is affecting the stiffness of the material. So we can see that for at very, very low confinement stress, the effect or the line is typically horizontal. And we can also see that in coral sand when we have a high 100 kPa. When we increase the confinement, we see a slight effect of a greater effect on the stiffness of the material that we can identify somewhere here. So in other words, the confining stress is important under these conditions. Now, in these four main pictures, we can see the big deviator stress in all conditions. But here we have a strain rate for silica sand and coral sand for two different confining stresses, and we can also see that the peak deviator stress, so the maximum, the final strength at the end, so this peak, right, is also moving as the strain rate is being identified. In these two figures, we see something special. We have the peak deviator stress, but in the horizontal axis, we have the strain that corresponds to the maximum or to the peak stress. For silica sand, we see that, if we go back, we see that the peak is moving backwards as the strain rate increases. However, for coral sand, it does the opposite. So as the actual strain corresponding to the maximum stress increases, from this point to this point to this point to this point. So in this case, the strain to peak stress is increasing, whereas here it's decreasing while the strain rate is increasing. Now, based on all of these experimental results, the idea was to develop an empirical model that is based on the equivalent strain energy density concept. And this concept is very well known. It's been used in material science, in mechanical engineering, in civil engineering. And in this case, what it says is that if I have two stress strain curves, same material, loaded at different strain rate, epsilon 1 that 1 and epsilon that 2, there is some point where these two areas are equal. Right? Obviously, this magnitude of the axial deformation is going to be less than this one, according to what we saw earlier with this loading stress strain curves. Right? Now, if these two are equal, what's going to be different is the axial deformation. But we don't need that. We wanted to have the same axial deformation and see how these curves change, and based on what the curves are changing. That's why we find, or we take this exponential m value. Right? So making a relationship between the two areas, right? There is an m value that at the same strain level, right? This m value is going to affect the stress strain behavior. And also, as a result, we run this approach or this model for uniaxial compression testing in these materials. And we also run this model to predict rate dependency in triaxial compression tests. These are two existing publications right now. That was the work of the last specifically. And basically what we have here is, we see in the upper left side of the screen, in one-dimensional conditions, as we saw earlier, the load is increased, the material is being affected, but there is never a failure of the material as a whole. Whereas for these, we see the peak deviatoric stress. So the area under this curve can be defined as a strain energy density, and the sum, the addition of the small slice for each one will be, in this case, U sub U, which is the cumulative strain energy density. So again, having this relation between strain rates, axial strain, and axial stresses, right? I was able, we took this from the literature, right? That this m value can be found by developing this analytical part. And what I did, although it might look silly, having log on both sides, the main idea of this is to go through this, right? In order to linearize these functions. The log of m, again, m is this exponent, right? M is this exponent, and m is going to vary depending on the axial deformation. For this material, for silica, for example, I found this relationship with m, which is functional axial strain, or we can call it porosity. We can call it also void ratio. And by fitting a linear term here, or a log term here, we find out values of A and B for this function. And now this m value is going to go back, and then we remove the log, and we get something like this. Two different curves for coral and silica sand with two different constants, A and B. But then, at the end, that m value is going to be somewhere here, and we can find out the prediction of sigma p. Sigma p is the prediction of the stress. If we know already an existing strain rate, and if we want to predict this axial stress at this value, By using this epsilon, which is the actual deformation, we can make predictions starting from obviously the quasi-static condition, and we can go even higher. So from 0.01, 10% per second, 100% per second, 1,000, and even higher. Obviously, this is going to have a limitation, which is, I'm going to explain it later on. This is for silica sand, and this is the result for coral material. The same expression, this value will change, but we have this this prediction of now. Obviously, for 100 and 1,000% per second, we don't have the right equipment to do that. I mean, not in the by using the hydraulic frame. That's what I came up with by working with the drop weight machine that Professor Gupta gently
allowed you to use,
allow me to use, and also with the help of Stephen. I noted, I calculated different drop heights, right? By using the maximum load or the maximum weight that these frame can house, which is about 13.5 kilograms. And by using a thickness and varying the thickness of the sample, I was able to achieve even higher strain rate of strain behavior at very high strain rate. Again, the prediction versus the experimental result. Here, the black line, or the black solid line, correspond to the predicted output, whereas the red line, the red dashed ones, are experimental work. Obviously, as we go higher and higher and higher with the strain rate, we will see some some peaks up and down. So I was working like for almost a month, trying to identify where these peaks corresponds to the real behavior of the material, and this is what I came up with. So if we can see the prediction or the model is provides a very useful and well results for applications from quasi-static to low, intermediate strain rate. But when we go higher, especially in this material, I don't know if you are able to identify this curve. It doesn't even go and follow these two lines. It goes back. And it shouldn't do that if the model at this strain rate is applied, like is used. So in other words, okay, the model is useful, but when the strain rate regime is not as high as very high strain rate. Now, for the traction compression test, remember we had the previous curves for uniaxial compression. Now for the traction compression test, one of the additional variables are sigmas, right? The confining stresses. So obviously the tests are set to be loaded at different conditions. So what we can see here again, this is log, this log-log relationship. The log of M versus the actual strain or porosity or void ratio is shown somewhere like somewhat here. We can see here, from these three plots, A, B, and C, that at very low confining stress, the dispersion of the results are wide. As the confinement is increased, we can get some narrow results. And that can be also seen here in this figure when M is getting rid of the log function. So the red line here is the material, is the behavior of the material loaded at very low confinement 100 and increases, and it goes up and up for 200, and it's much higher at 400. Ideally, based on what I saw with all of this analysis, ideally for material, especially for sand, with no rate effects or conditions that don't provide rate effects, this line should be a horizontal line. So obviously this is based on all of these experimental results, but ideally it should be a horizontal line in this case. And now I got these A and B constant values for 3 different conditions of confinement. And I go back and see I only plot here 400 kPa because for 100 and 200 there's not much of rate effect. And now for 400 kPa at 0.1% per second, we can see these 2 lines that are close to each other. For 400 at 1% per second, we also have a good match between those 2, and at 10% per second as well. I got this plot of 1000% per second based on results that came from the drop weight test. And again, so I had to take the data that were not supposed to be part of this test because it might be the sensors of the velocity that started early, like when you drop the weight, you have to set a flag or a sensor that starts taking the impact velocity. And sometimes these curves before the starting point will give you like weird results that might not be included or that I didn't include. Obviously, this model has limitation, and again, there is room for more investigation. The editorial board member of the journal where we submitted these 2 publications, he wrote back to us and he says that this looks promising and that he wanted to see more results in the near future. We'll see how. So few limitations of the model. Obviously, the more or the higher the strains we apply, the more invalid the model is going to be. However, the model captures a non-linear response as the strain rate increases by using a piecewise definition for viscoelastic behavior altogether. So it says that the model captures or wraps different conditions within the entire experiment, such as elasticity, rearrangements, and particle damage of the behavior. So again, I think this is similar to this. The approach provides the response and it shows the behavior as a whole without distinction of what part of it is of the model is governed by elasticity or by elasticity or rearrangement of the particles. And the model seems to provide accurate results at a strain rate up to maybe a little bit lower than 1000% per second. Now, after the modeling, I wanted to see also the role of the particle breakage by conducting an experimental work. Again, in uniaxial compression test. 2 different materials, 2 different aspect ratio, or in other words, 2 different geometries. AR stands for aspect ratio of 6, means that 6 times is the diameter compared to the thickness of the specimen. So for an aspect ratio of 6, I have the same mold. For an aspect ratio of 1, we added like a picture in order to create again the diameter and thickness dimensions the same. 2 different strain rates in this case. One of the slowest we could get by using hydraulic frame, and 10% per second is the maximum. Arrested strains. Oh, the main idea. I'm sorry if I without explaining this. The idea was to choose specific strains where the samples will be arrested in order to what? In order to identify crushing of particle damage and the extent to which deformation is localized. So in other words, where in the plots, in the stress strain plots, we can start identifying particle damage. That's why we had arrested strains from 5, 10, 15, 20, and 30% in very dense material. Again, 2 repetitions and 2 aspect ratios for a total of 40 well specimens. Okay, so and these are the average of the results. This is for coral sand. This is for silica sand. Sorry if I didn't label the figures with the names of the material. For aspect ratio of 6 and for aspect ratio of 1. One of the main ideas to conduct tests with aspect ratio of 1 is that we were able to achieve very high axial stresses. If we can see here in the left side of the screen, the magnitude might not go up to 80 megapascals, but for a smaller diameter, right, samples that are subject to this load, we can go up to almost 600 megapascals. So with this aspect ratio 1, we were able to see more phenomenal models. So the red dashed line corresponds to a slow test, to a strain rate of 0.01, and the black solid lines are related to 10% per second in all of them. If you see here, for example, this is a 5% arrested test, 10, 20, and 30% in both materials, in silica and corals. And then, based on that, we were also able to quantify the stiffness of the material by taking measurements at different points. For example, the initial modulus, which is what you can see here, is the initial modulus that runs around 0 up to 2 to 30%, which is where elasticity is acting. The secant modulus, which is measurement taken from 0, from the origin, up to the maximum axial stress, and the pseudoelastic modulus, which is the rebound or the unloading behavior of the curve, right? So we were able to see something like this, something similar behavior that is quite horizontal, another ones that are slightly increasing due to the strain rate effect, slightly increasing. The secant modulus obviously is going to change because we take measurements from here up to, if we arrested the experiment at 5%, from here to 10, from here to 30%. So these values are going to change and I'm going to increase unless we use aspect ratio, large aspect ratios. Large aspect ratio means low axial stresses. With low axial stresses, the sample is not experiencing much change. We also have this a similar behavior of these uniaxial loading and unloading, but instead of having axial deformation, we have axial stresses. So what's the idea? Again, initial moduli, which is again the first part of the curve, the secant moduli, and the pseudoelastic or elasticity moduli taken and measured in the loading curve. Obviously, a slight increase, and it's due to the strain rate condition, as we saw initially. The secant modulus of the secant moduli of these two materials, silica and coral sand, with aspect ratio of 1, will increase after some point, and after like 100 megapascals is reached. Whereas for these two, the small triangle ones, which is aspect ratio of 6, the secant modulus is typically flat or horizontal. And the pseudoelastic moduli also showed us that there is a main distinction of the materials that are loaded in those two different aspects. These two small samples and these two large samples. This is a summary or like a, not summary, a detailed plot of the evolution of the stress strain behavior, size distribution, and aspect ratio. At 5%, 10%, 20, 30% of samples loaded in with an aspect ratio of 1, where we don't see particle damage at all. At 10%, the material starts experiencing some damage. At 20%, the damage or the torsion is being identified better, and at 30%, the particles of the sample are significantly crushed. And whereas for the aspect ratio, we see that along all of these conditions, except for this one, the aspect ratio remains the same. So it says that we can conclude that although the particle is broken, it might keep a similar aspect ratio from the parent material. And then by using a Harding's methodology to quantify particle damage, which is this one, which is VR, the relative breakage is the relationship between the total breakage of the sample at any given stage divided by the potential breakage that the material might have. So from this point up to this point that we set, we valued 10 microns. This is the potential breakage. This particle, this initial size distribution can shift all the way up to here if a significant amount of load and time is applied to the material. So at the end, this relationship, this VR, is done, and then we can quantify as, again, could be arrested strain. We can change it also by saying it could be porosity, the change of the porosity of the material, or void ratio, or speaking in terms of geochemicalism. What can we see here is obviously an aspect ratio of 1 depicts more damage than aspect ratio of 6. The maximum at the end, at the 30% of arrested, we only have like a 10 or 12 percentage on the relative breakage. Whereas for this material, silica material, a very, very high loading, which we got something similar to 35%. In coral sand, we got something similar. Higher here, lower here. I'm sorry, this is silica and this is silica and this is coral. When we plot the relative breakage versus actual breakage. And here we see the relative breakage versus actual stress. This is interesting that in the initial part of the test, when we load samples at up to 100 megapascals of loading, those two results might be similar, and then we get something like a value 12, 13. But now, by using smaller samples, obviously there is more actual loading, and the specimen is going to go somewhere like this, and I'm expecting to have like a plateau somewhere here. But even if we keep applying more loading from from 360 up to almost or a little bit more than 500 megapascals, the damage is not evident. Now, I'm wondering what might happen if we keep going and up and up and up. It might get something like this. It might show a parent like this. It's gonna go here and it's gonna go up. So, and something similar happens to the other material. See, after 188, we get something like this. But here in this case, we get more flatter response, like here. So I want also to have how the diameters of like two selected diameters, D5 and D50. From the original material, right? How the particle changes and evolve into obviously smaller sizes, right? Here we have these diameters versus actual deformation or arrested deformation, and here we have the same diameters versus actual loading, actual stress. We have D50, which is the red plot, and we have D5, which is the blue ones. For this, for silica and for coral sand. And then we can see how, and at what point of deformation the material starts experiencing more damage. So we can see that right after 10% per second, I'm sorry, after 10% of deformation, the material or this curve changes its slope, and we can see it is more evidence of damage after this point. And the same happens when we have the 50. Obviously, it's not going to break more than these ones, but it will show some damage. And something similar is happening here. Again, after 50, almost 80 megapascals of stress, the damage is observed. Now, what I did here was I normalized diameters. Existing diameters divided by its own maximum diameter. In other words, if we have a zero actual strain, is the original material, is the material. That's why every single point or every single line starts at the origin, which is 1, right? Now, after the sample is being loaded at different, again, arrested strain 5, 10, 20, and 30, we can see that this normalized factor is being reduced. What reduces more? The larger or the smaller particle? I thought initially that the larger particle was going to break more. But look up if we have these values. This is 1, and this is this 75. This 75 corresponds to the 75. If it is 75%, that corresponds to is the diameter at which 75% of the material is smaller. It is smaller than that opening. So we have 75. In other words, this material is larger than this one, This 75, this 25. This is the median average, D50, and D5. The reduction of the material is greater when you have a smaller sizes. And it happens in all of them. It happens in all of them. It happens in silica and coral, and it happens in both aspect ratios. And the same with this normalized diameter by taking the actual stress. We wanted to do this in order to see if there is a distinction between plotting the data versus strain or stress. But we saw something similar. The smaller diameter or the smaller the diameter particle produces more than the large one. An interesting observation. Obviously, if we have this is an ideal condition. In this in the actual mold, We have materials of different sizes, right? There is actual load being applied. We have these boundary conditions that prevent radial deformation. And all of this external load is going to be transferred through all of this via chains that internally form. Now, this is a coordination number of point A, of particle A, and this is coordination number of particle B. I counted A here and B here. Why? This particle is larger than this one. It has more neighbors. Right? So when it has more neighbors, the energy is being transferred more equal. That comes from top, and it's going to be transfer the energy in all different neighbors or contact points. Not in the same magnitude, not in the same level, but it's going to transfer that energy more than when you have a smaller particle that might have obviously less contact points. When we have this reduction, and when we have this hypothesis, and when you have like also a particle size analyzer where you can identify shapes, sizes, you can gather images from the specific materials, like you see this. It is coral sand at aspect ratio of 6, coral sand aspect ratio 1, and silica 6 and silica 1. By choosing a specific diameter of 90, 60, 30, 10, and 5%, and arrested strain starting from obviously 0 strain, which is the original material, 5, 15, and 30, and here 5, 10, 20, and 30, we will see the evolution of the particle. I have to mention that this particle right here is not the same one as the ones lower. These particles are random particles that carry these similar conditions. That B90, right, is being identified. That the aspect ratio that we saw is identified. So for the next ones, these lower ones might not be, or this one might not be this one after the evolution, but these particles, these smaller particles, corresponds to particles that possess these conditions of B5, B10, and B5. So we can see from top to bottom and from left to right how the particle is moving and is reducing its size. And also at the end, by using a variable, like a simple analysis of variables, I wanted to also point out or identify what variable influences more in both main conditions. The change in the mean stress of this stress-strain curve and the change in the particle size. So how the particle size reduces. And what variable is more influenced? So we have aspect ratio, obviously. We have axial deformation, or again, it could be porosity, it could be body ratio. And we have a strain rate from 0.01 to 10% per second on both materials, calcareous material and siliceous material. So from this left figure, we can see obviously that the axial deformation of the porosity, right, is influencing more the change in the mean stress more than the strain rate. So I was expecting to see something like this, a change of the behavior of the stress-strain behavior, also the stiffness of the material, but not that much. Aspect ratio is also important, but this too. Plus here, the reduction of particle size, how the particle moves again from the original size to smaller sizes, is mainly governed by the aspect ratio and the porosity of the body ratio of the material. Whereas for the strain rate, there is no summary and conclusion. You might have a summary in the printed copy, also Dr. Arun, but I skip those. And the conclusions that I found in uniaxial compression conditions, there is a distinct measurable strain rate effect for silica, sand, and coral sand. However, the material, which is not fully investigated in detail, plays a significant role. That increase could be 25% or up to 25% in strength and stiffness. In reaction compression case, the role of the strain rate depends mainly in, at least from this study, in confining stresses and the density of the material. Which means that when the sample is highly confined and is prepared at very high density, there is more options or more chances that the strain rate will be observed. And from the particle breakage approach, the onset of nonlinear strain softening behavior, and it is observed in the third experiment, correlate with the progressive size reduction observed in these arrested tests. It was seen important that smaller particles break more than larger particles. People in the who have been working with the particle breakage, modeling of particle breakage, have found similar, not that many. I found one study from ENA that he pointed something similar to this. So I was really delighted and really curious about how this study, not right now, but in the future, how this is going to provide more interesting outcomes. Sand fractures typically following aspect ratios of the parent material. When we model strain behavior in axial compression and axial compression test, we can see that the ACD model is appropriate to extrapolate this strain behavior to scenarios for strain rate dependency up to, I forgot to, not up to a specific value of a strain rate. Say greater than 100% per second, but maybe less than 1,000. And then suggestions for future investigation based on what I have been talking to some of you, and suggestions that came from reviewers from our publications. Quantification of particle crush. This is something that definitely people are working on right now. Discrete element model. So far, there has been a number of approaches that are being used to validate experimental work. However, these models still have limitations. For example, you have two particles that are against each other. The breakage is not conceived as a breakage of the particle, but as a join of two materials, of two elements together. The quantification of that might not be clear yet, first. And second, in different conditions rather than uniaxial compression test, the volumetric change might not be easy to quantify. In other words, the dilation of the specimen loaded. When we have the modeling, might not be easy. And global versus local measurements on high strain rate fractal testing. A few studies recently, or not recently, like 50 years ago, but nothing than that, which gives room to keep working on identify the difference between global measurements and local measurements in fractal conditions. Mesoscale measurements of unilateral interaction test. We have Suescun that have been working with transparent materials. I think the use of transparent sand and the design of the different chambers of molds to easier identifying these mesoscale behavior, which is important. Thank you. Before starting questions, I'd like to acknowledge my committee. Thank you, Dr. Alexander, for your endless support. Dr. Velez, thank you. Dr. Adun, Dr. Hussein, and Dr. Sulta, for the entire civil and urban and engineering faculty and staff, definitely. All my PhD and master students and colleagues. Special thanks to Materas, Camilo, I've been working at Steven, Ivan, Mary, Sina, and family and friends. Family, I don't understand my Johanna, Matilda, and Lucas, and my mother, my sisters, and my friends. Yeah, with that being said, thank you so much. And
we'll take one or two questions from the students, then I'll ask you to leave.
Okay. I have a question regarding the triaxial test, the rate effect of sand in triaxial compression. I know you had one of your conclusion is under high confining stress, you kind of have a very strong strain effect. What can you say? Do you do anything about? Does that effect applies to critical states of the sand too?
No, it doesn't apply to that. It doesn't apply to the critical state. Sorry. It applies to the initial portion of the behavior, right?
So just the peak stress.
Elasticity, elastoplasticity, yielding stress, and typically the peak vibratory stress. But at the end, when the material falls down to the ultimate stress, I think it's very not likely to be distinction. It could be that the experiment shows some sort of a differences between those two, but I don't think it's unique. I don't think that it creates an significant effect.
Okay. And also is like based on that figure that you provided, there's one figure which is rather counterintuitive. It's you have a very loose sand under high confining stress, and then you showed some sort of peak strength, which suggesting there is a dilation, which, you know, for loose sand and high confining pressure, really shouldn't say that behavior. Do you have an explanation for that?
Typically the non-dilation is mainly observed when material is loosely prepared, and also when the material is loaded at very long time, right?
This is not very loose. This is 55%.
Yeah,
But
like,
still under very 400 kPa, which will suppress all dilation at all.
It should suppress dilation.
So it's just very surprising to see.
It's slide number 17. Well, conventional wisdom is based on a few tests. He also, the biggest thing that he says that is not conventional wisdom is that smaller particles break more than big particles. Everybody says, historically says that big particles
should break more. That's what. But then
nobody had these kind of measurements before. So.
oh, you mean here, right?
Yeah.
Yeah.
Well, I think with at this confinement, I mean, it's not the greatest confinement ever. I saw a study that goes up to 2 megapascal of confinement. But I have seen in the literature that at great confinement, even if the sample, actually, this is not typically loose, it's medium dense. that at this stage, under these conditions, you will see something like this. Not specifically like this one, but you will see some sort of initial small dilation at the beginning.
Yeah, but the behavior is consistent, at least at the average of 3 tests each.
Yeah.
Yeah, I'm just it's
Yeah,
surprising,
it's surprising, yes.
to see.
No, yeah.
Yeah, just one last question is regarding your you said small particle breaks more, and I think you provide a explanation is because there are less contact points.
Yeah.
So can you explain a little bit why you assume what is your base on?
This is right. This is the hypothesis, right? This is what I.
Because generally, you know, in some of the physics papers that I read, they will say have more contact points would create means more force. The particles are more likely to break.
Right.
So you said less
cushion.
contact points.
Yeah, I said the opposite. Yeah, it will be a good contradiction. Okay, yeah, right. So the hypothesis is the opposite. So you have these two particles, right?
Yeah.
Those particles are different in size.
Mm-hmm.
So this one is going to have less contact points, right? If it has less contact points at this level, for example, the external loading, right, is being transferred ideally uniformly or at the same level across this line, right? So now the difference here is that when you have a greater size or material with larger size, you have more points for the particle to pass the energy to others.
So you assume that the load applied the same. You have less contact point, means you have more stress. That's
yes,
that's what,
that's what you're
right,
saying.
That's what he said. But
wouldn't you
but
normally
to correct you,
uniform stress?
the hypothesis is based on a bigger particle will have more flows.
That's
That's the hypothesis. But this is the opposite of his measurements.
Yes, but the only way that you say that less contact points will lead more particle breakage will make sense is you assume the force is uniformly applied.
Yes.
Then you divide by the less area, so
Definitely.
more stress.
Right.
That's why it causes more particle breakage. But generally, you would assume the stress is uniformly, effective stress is uniformly applied. Then that would conclude to the opposite. That means you have more contact points would result in more force on the particle, would lead more particle breakage.
But okay, yeah, I get your point, and it's interesting. It's valuable. However, think about regardless the stress that these two particles are being experiencing. Just imagine the load, right? The load that this particle, right, and the load that this particle. So this load is gonna be. It has to move. It has to pass from this point to its neighbor, right?
You assume the A and B particle A and B experience the same load, right? Then you divide by the contact surface. So obviously, more contact surface would give you less load,
right?
Yeah, which would agree with your your conclusion.
Right.
But I just thought generally geotech when you do effective stress would assume the stress is constant.
But nobody had measurements like this before.
Yeah, this is something like new, but obviously.
Yeah, I just think probably you need to look at it more, because
the reason could be something else, but the measurements are.
One of the reasons you would say is I don't know how you did the sieve analysis when you're crushing, because
not sieve.
It's not like it was.
But there are very fine particles which are lost during because we didn't buy the one that give
the entire sample was poured into the size analyzer.
But I thought the size analysis has a limitation on what size it can capture.
Yeah, the limitation is 10 microns and even less because it could go up to 5 microns. And
So which is significantly smaller than anybody else who's in the field.
Of this material.
So I agree with what you said is conventional wisdom, but nobody has measured it with such accuracy before.
Yeah, but I'm just saying, if you're gonna, it's observation is one thing, but if you want to provide a
And explanation
for
could
it,
be something else.
yeah, it
Okay.
could. It's
Yeah,
very,
it could be, yeah.
you know, you make a big of explanation for something that very.
It could be something right, but this is my understanding of the problem, the final conclusion that I get out of the analysis, right? But definitely it could be something else. Yeah, Professor.
Well, isn't
All
it,
right, I'll ask the
isn't it
students to go.
possible-
I'll leave the committee so that we keep the time. Nick, how are we communicating with Professor Abdul?
Is he still with us?
Yes.
Of course.
Professor?
Abdul, are you there?
Yeah, I'm still here.
Okay, good.